This is the model that is the framework that we'll be looking into, right? So we just got started with this model in the last lecture, if I remember correctly. Now, the thing is, why do we need this model? So, a key property of this particular class of endogenous growth models is the absence of diminishing returns to capital. So why do we need diminishing returns to capital? Basically, we need diminishing returns to capital because otherwise we would not be getting positive growth in the long run, right? So positive growth in the long run for per capita variables is something that is needed, right? So we would want to have sustainable long run positive growth. One way of doing it in the solo model was to incorporate technology, right? So exogenous growth in total factor productivity would entail a growth of per capita variables in the long run, right? So the question is, without the use of exogenous technology, because exogenous growth of total factor productivity is kind of an ad hoc assumption. So without this, if we, if there is no external factor, so to say, no external shock that is in action, in absence of such external factors, of external shocks, would we still manage to get positive growth in the long run? That is the question. So one way of ensuring that is, completely getting rid of the diminishing returns to capital property, right? So one way of getting rid of diminishing returns to capital is to endogenize growth, is to basically ensure that the growth process would be possible from something that is endogenous to the theoretical framework, right? So when we are talking about endogenous growth models, this is the simplest form of endogenous growth models. This is, the technology takes the AK form. What you would notice is that, because of certain actions which are endogenous or which are internal to the model, accumulation of capital and investment in capital would be made possible, and this endogenous accumulation of capital and investment would in turn give rise to growth in the long run. Okay, so basically key property is the absence of diminishing returns to capital, right? So if we can ensure absence of diminishing returns to capital, basically we are home free. We can basically go on to show that a positive long run growth would be possible. Now see, the simplest version of production function without diminishing returns is this, right? Because see, the AK, K denotes aggregate capital, Y denotes aggregate output, okay, and A is basically, it's a parameter, it's a positive constant which reflects the level of technology. So basically the global absence of diminishing returns, it may seem more plausible if we think of capital, aggregate capital, that is, in a broad sense, which also includes human capital, right? So this type of production function, actually this was this first came into being long before the development of the endogenous growth models, the endogenous growth literature. This actually the first person to use such a production function was von Neumann, who did who had a lot of contributions in computer science also. So he first used this kind of a technology or a production function in I think in the 1930s. So that was around the same time that Keynes came up with his very famous work on money, interest rate, and income. So anyway, so the bottom line is that this sort of production function, this sort of technology has been there for a long time, right? It's just that it has been put to use in the endogenous growth literature comparatively recently. Okay, so basically the idea is that in the economics context, the idea is that K incorporates a broad understanding of capital, right? So, the basically when we think that there is no diminishing returns to capital, this might seem a little unrealistic, but if you think of capital in a broad sense, or capital that definitely includes human capital, then this idea would become more plausible, right? So output per capita in this sense, becomes very it's very simple to find out output per capita. Output per capita would be small y equal to a times small k, right? And average and marginal products of capital are also constants, because what is your average product of capital? Average product of capital is total output divided by capital, which is a, and marginal product of capital is partial derivative of output with respect to capital, total capital, which is also a. Okay, so both average and marginal products of capital are constant at the level a, which is positive. Okay. Now, if we refer to our basic Solow-Swan equation in equation number 19, then that just we'll stick to that basic equation, and in place of average product of capital, which is Fk by K, we are going to use our new expression for average product of capital, which is Fk by K is equal to A, right? So if we plug in that relation, that Fk by K is equal to A in the basic Solow-Swan equation, then this is what we would obtain, right? So now basically, see, we in a way we have returned here to the case of zero technological progress, because x, which is the rate, in the Solow model with technological progress, x was the rate at which all per capita variables ultimately grew, right? So that was the growth of rate of growth of technology, total factor productivity. So here, in the AK framework, we are doing without technological progress, in the sense that in this particular framework, small x is equal to 0, because we basically want to show that per capita growth can now occur in the long run even without exogenous technological change. That is the whole idea, that we are basically we are keen to figure out whether we can reproduce long run positive growth rate even without technological progress, or even without exogenous growth of total factor productivity. That is what we want to figure out. Hence, in this sort of a framework, you find x to be equal to 0, right? So that's the basic idea. Now let me show you the graphical representation of this model. Now for the graphical presentation, basically see the main difference. The main difference is that the downward sloping savings curve, in the previous framework, there was a downward sloping savings curve, in the sense that the SFK by K schedule was definitely downward sloping, right? See, this was definitely downward sloping. But in the AK model, SFK by K, that would be equal to S times A, which is a constant. So your SFK by K, that is the savings schedule, would be S times A, and that would be a horizontal schedule, right? And basically, this is the main difference, that the downward sloping savings curve in the previous setup, that is in the Solow-Swan model, is replaced in the AK model by a horizontal line at the level S times A. Okay. Now the depreciation curve is still, it's the same. So earlier, what was the depreciation curve? This was the depreciation curve. This was with some additional factors, of technological progress. So anyway, just ignore this. But once again, this was the effective depreciation curve in a way. So that was horizontal as well, and here also it would be horizontal, right? N plus delta. Here x is equal to 0, so the effective depreciation schedule would be n plus delta. Now see that we have the depreciation curve as the same horizontal line, which is n plus delta. We have, the same, a different savings curve, which is a horizontal line at the level SA. Now, the vertical, see, this is the idea that the vertical distance between these two lines, the vertical distance between the SA line and the n plus delta line, this vertical distance gives you, from the basic Solow-Swan equation, what is the difference between these two? The difference, once again, something that is captured by the vertical distance, that is, the difference between SA and n plus delta, that gives you the growth rate of capital per person, right? So notice here that the growth rate of capital per person, which is the difference between these two schedules, that is a vertical distance, and this vertical distance remains constant. This vertical distance, if you call it gamma k, this gamma k is the same, right? Throughout the different levels of capital per person, we have the same value of gamma k. That is, we have the same value of growth of per capita capital. This is something new. So I repeat, k dot by k, which is the growth rate of per capita capital, that according to the basic, in the Solow-Swan equation, that was the vertical distance between these two lines. Here we are doing with essentially the same framework, but here we don't have a technology. In the simplest version of the Solow-Swan framework, also we did not have technology. Only difference from the Solow-Swan model is that we are using a different technology, right? We are using a different production function, right? So because of that, because of the sheer nature of the production function, we have a horizontal SA schedule. And because of that, another crucial difference that crops up is a positive growth rate of capital for all values of small k, right? This is something that we were never able to achieve in the Solow-Swan model, right? So k dot by k, which is vertical distance between the SA line and the n plus delta line, this vertical distance is constant, it is positive, right? And basically it is positive for the case where SA is greater than n plus delta. So that particular case is being depicted in this diagram, right? So for SA greater than n plus delta, we have k dot by k to be positive, to be greater than 0. Now, since the two lines are parallel, k dot by k is constant. In particular, k dot by k, that is growth rate of capital, is completely independent of k, right? So k, small k, can take any value whatsoever, but the growth rate of small k, that is the growth rate of per capita capital, would still remain positive, no matter what value small k takes, right? So so these two lines, these two schedules are parallel, hence growth rate of capital is constant and it is independent of k. Therefore, small k always grows at the steady state. This is the main finding, that the growth rate of capital here is positive, whereas in the basic Solow-Swan model, we found that the growth rate of capital was 0, right? So at the steady state, what happened was SA would have been exactly equal to the effective depreciation, and that ensured that k dot by k would be equal to 0. So in the steady state, we had 0 growth rate of capital, whereas that happened in the Solow-Swan model, whereas in the AK model, we have a positive growth rate of capital in the steady state. Okay, so this is the main difference. Now, see, the capital grows at the steady state at, let's say, we call it the growth rate of capital, that is, let's say we call that k dot by k star. Star as in, since it's a variable at the steady state. So any variable at the steady state, we denote it by with a star superscript, right? So here also growth rate of capital is denoted by K dot by K star, and this is the expression for that. The expression for the growth rate at steady state is this. It's basically the difference between the two schedules as was just shown, right? So this is your growth rate of capital. It's positive and it's a constant. So the interesting thing to note here is that since y is equal to ak, y dot by y is equal to k dot by k at all point in time, right? In addition, consumption is a fixed proportion of income, right? So consumption is exactly equal to 1 minus s times small y. So small c is equal to 1 minus small s times small y, right? Consumption per capita is 1 minus small s times output per capita. C dot by C, which is which is the growth rate of consumption per capita, that is equal to K dot by K. This thing also applies. So basically, what do we notice here? Something that is a kind of an unique result is that y dot by y is equal to K dot by K. And C dot by C is also equal to K dot by K, right? So all per capita variables grow at the same constant rate, right? Which is given by this. So in the long run, at the steady state, all per capita variables grow at the same constant rate that is given by this. So growth rate of output per capita is captured by this. Growth rate of consumption per capita is the same, and so is growth rate of capital per capita. Okay, now this is the basic result that emerges out of the AK model. One very crucial result is that capital output and consumption, all these variables, basically they are growing at the same rate, but more importantly, more crucially, the growth, this rate of growth in the long run is positive, right? So even without exogenous technological change or exogenous technological progress, we are still able to reproduce a positive growth rate for each of these variables, capital, consumption, and output. For each of these variables, at the per capita level, we can get positive growth rate in the long run. Okay. Now, note one thing, that an economy that is described by the AK technology can display positive long run per capita growth without any technological progress. Moreover, the per capita growth rate that is shown in that's shown by equation number 43 here. This depends on the behavioral patterns or the behavioral patterns of several parameters. So see, this was earlier equal to 0. Now it's a constant, and it's basically dependent on a bunch of parameters, right? So the growth rate, the long run growth rate for the AK model depends on the behavioral parameters of the model, including the savings rate, the A, which denotes the technology parameter, and also N, which is the rate of growth of population. So unlike the neoclassical model, a higher saving rate here leads to a higher rate of long run per capita growth, gamma star, right? So if we have a higher S, then our long run growth rate of per capita growth rate of output, that would increase, right? So the thing is, with the AK production function, we can never get the kind of inefficient oversaving that is possible in the neoclassical model. So for example, a shift at some point in time to a parametrically higher value of, let's say, S, basically means a lower level of small c at that particular point. But a permanently higher per capita growth rate, gamma star, and hence higher levels of small c, that, these would follow after some future date. So this particular change cannot be described as inefficient because it may be desirable or undesirable depending on how households discount future levels of consumption. So that basically depends on whether you are a risk averse or a risk neutral person or a risk lover. So it depends on the saving patterns of different households, right? So similarly, if the level of technology, that is A, if that improves once and for all, or if the elimination of a governmental distortion effectively raises A, let's say, if because of that A increases, removal of government distortion, that can increase A, then of course the long run growth rate would be higher. Now, changes in rates of depreciation delta and population growth n also have permanent effects on the per capita growth rate, right? So all these follow from equation number 43. Okay, now if we do one thing, if now the thing is, unlike the neoclassical model, the AK formulation does not predict absolute or conditional convergence. This is another important result that follows. That is our, del y naught by, del y dot by y, which is, del y dot by y divided by del y. That basically means the partial change of the rate of growth of output per capita with respect to output per capita, right? So as you keep on increasing your output per capita, does the growth rate of output per capita increase or decrease? In the AK formulation, it's very easy for us to check that del y dot by y, del y is equal to 0. And this applies for all levels of y, right? So this is one thing. So this del y dot by y, del y is 0. So if that is the case, then if we consider a group of economies that are structurally similar in that the parameters, the different parameters are the same. Like the parameters S, A, N, delta, these are the same. Let's say. So the economies differ only in terms of their initial capital stocks per person, which is K naught, and hence basically if the initial capital stocks per person are different, then of course the initial output, initial level of output and the initial level of consumption would also be different. So y0 and small y0 and small c0 are also different across different economies. So since the model says that each economy grows at the same per capita rate, gamma star, regardless of its initial position, so the prediction would be that all economies grow at the same per capita rate, right? So this particular conclusion, the conclusion that all economies grow at the same per capita rate, this reflects the absence of diminishing returns. So another way to see this result is to observe that the AK model is just a Cobb-Douglas model with a unit capital share, that's alpha equal to 1. We can think of it that way. So see, k raised to 1 minus alpha, L raised to alpha, that was our simple Cobb-Douglas technology. So here it's just AK model. If you just plug in alpha equal to 1, you would be able to reproduce capital Y to be equal to A times K. So once again, if you do that, and if you do the analysis of convergence in the previous section, and if you do the same here, then what you would find is that the prediction is a substantial, sort of a drawback of this model, because conditional convergence is not possible in the AK model, right? Because conditional convergence in the previous model, conditional convergence in the solo model, was an empirical regularity. However, in the AK model, this is something that we have to do without. We cannot reproduce conditional convergence. Maybe with some minor changes, we would be able to reproduce conditional convergence for maybe for a specific range of capital, let's say. So, but that is not something that you can establish as a general rule. Okay, so basically, one way to think about the absence of diminishing returns to capital in the AK production function is to, as we saw this earlier. One way to think of the absence of diminishing returns to capital in the AK production function is to consider a broad concept of capital that encompassed physical and human components. So later on, we consider, like, in more detail, theoretical frameworks and models that allow for these two types of capital, that is physical capital and human capital. So models would make a distinction between the two. Okay, so other approaches have been used to eliminate the tendency for diminishing returns in the neoclassical model. So see, it's sort of like a trade-off. So in the AK model, getting rid of the diminishing returns to capital property is a priority. So in order to do that, you have to allow this particular result that follows, that there won't be any conditional convergence, right? But still, with some, if you tinker along, tinker a little with the parameters, if you do a little bit of modification with this model, still you would be able to reproduce conditional convergence to a certain extent, right? So how that can be done, we can look into that later on. But let's try to understand the basic idea behind this model. So the good thing about this model is that it can reproduce positive growth rate without technology. And how that is made possible? That is made possible through the sheer absence of diminishing returns to capital. So this model, number one, the good thing about this model is it gets rid of the diminishing returns to capital property. Number two, it can reproduce positive growth in the long run. These are the two positive aspects of this model. One drawback is that it cannot quite reproduce the conditional convergence, but still that can be taken care of if we modify the model a little bit. So the basic idea is that several approaches have been used to eliminate the tendency for diminishing returns in the neoclassical model. So this this tendency of diminishing returns in the neoclassical model, it's kind of like it's an undesirable property. So later on, a lot of much of the literature which has developed, which has emerged over the years, is to do with eliminating the tendency of diminishing returns in the neoclassical model. So later on, we would study the notion of learning by doing, which was introduced by Arrow in 1962, and it was also used by Paul Romer in 1986. So in these models, the experience with production or investment contributes to productivity. So basically what happens is the learning by one producer can raise the productivity of others through the process of spillovers of knowledge from one producer to another. So therefore, a large economy-wide capital stock or a greater accumulation of the aggregate of past production, a larger economy-wide capital stock, you can think of it as a greater accumulation of aggregate past production. The total of the past production or the accumulation of past production that that contributes to a much larger economy-wide capital stock. So that basically improves the level of technology for each producer, right? So consequently, diminishing returns to capital may not apply in the aggregate, and increasing returns are even possible, right? So if we are looking at a larger economy-wide capital stock because of learning, because of the process of spillovers of knowledge from one producer to another, then essentially we are looking at greater accumulation of aggregate production or aggregate past production, right? So the learning by one producer can raise the productivity of other producers through a process of knowledge spillover from one producer to another, and we are looking at a larger economy-wide capital stock basically because of greater accumulation of aggregate past production and improvements in the level of technology for each producer, right? So if these things happen, if the economy-wide capital stock increases because of improvement in the level of technology for each producer, then a consequence of that would be diminishing returns to capital might not apply in the aggregate. Keep in mind, we are talking about the aggregate, not we are not talking about the individual producer, what might happen to the individual producer, right? So we are looking at the aggregate level. So at the aggregate level, because of learning by doing, we can have an increase in the aggregate capital stock, and we can get rid of diminishing returns to capital at the aggregate level. Even increasing returns to capital might be possible. It's a theoretical possibility. So in a situation of increasing returns, basically each producer's average product of capital, which is Fk by K, tends to rise with the economy-wide value of K, right? So consequently, if that happens, if Fk by K increases with the economy-wide value of capital, then SFK by K curve, this curve over here, this would be, earlier it was downward sloping, right? But if K by K increases over time, SFK by K increases over time because of increasing return to capital, and because each producer's average product of capital Fk by K increases with the economy-wide value of small k. So instead of a downward sloping SFK by K schedule, we would have an upward rising SFK by K schedule, right? So the SFK by K curve would be upward sloping, at least over some range. And the growth rate K dot by K, that would be increasing with K in this range, right? So at least for some range of capital, for some range of capital per capita, we might have a positive growth rate of capital per capita, right? So, excuse me, if SFK by K, if we are looking at an upward rising schedule, upward rising SFK by K schedule instead of a downward sloping one, then at least over some range, you would have increasing K dot by K with small k, right? So that would happen over a certain range. That that's not going to be universally true, or that would not be true for each and every value of small k, right? So if SFK by K is upward sloping, then at least over some range of small k, we would have the growth rate K dot by K to be rising with capital over this particular range. So for this particular range of capital, this particular range of small k over which we have increasing growth rate of capital or increasing k dot by k, for this particular range of capital, the AK model would be able to reproduce conditional convergence. So these kinds of models, models with learning by doing, or models with positive spillovers of knowledge, these models predict at least some intervals of per capita income in which economies would tend to diverge, right? So actually here, instead of convergence, we are looking at conditional divergence, because the growth rate of capital is actually, it's growing, k dot by k is increasing with k. Earlier we showed that this the growth rate of capital, growth rate of per capita capital, it must be diminishing, so that the economy with that is starting with a higher level of capital, that would converge, that would the economy that is growing at a slower rate, that is going to converge with the economy that is growing at a faster rate. Or conversely, you can think of it as the economy that started with a lesser initial capital stock, that economy that was initially growing at a faster rate, the growth of capital for that economy was slowly falling over time. So much so that it would have converged with the economy that started with a higher initial level of capital and that was growing at a slower rate, right? So here what is happening is, since we are looking at an upward rising SFK by K curve with with positive spillovers, and if we can reproduce increasing returns to capital, then this curve can be upward sloping, and at least over some range we can have K dot by K to be increasing with K. Okay, and if K dot by K is increasing instead of decreasing, then we would be looking at a divergence instead of a convergence. So model would predict that at least some intervals of per capita income exist in which economies tend to diverge. So it is unclear, however, whether these divergence intervals are present in the data. So this particular theoretical result cannot be supported with um, with a lot of empirical evidence, because if you look into the empirics, if you look into empirical data, you would be definitely you can support the notion of conditional convergence, but that not so much conditional divergence, right? So this is something, so the empirical backing of this particular result is a little bit weak, but still this is something to think about. Maybe if you look into a data taking into account particular range of capital values, then probably it's still possible to replicate this result, right? So this is basically this these are the basic results that follow from the AK model. We talked about the the basic the basic results, and some of the some of the positives of the model, the fact that the model was able to get rid of diminishing returns to capital, fact that the model was able to reproduce positive growth rate of capital in the long run, and also a little bit of a drawback in the sense that the conditional convergence cannot be reproduced, but still something with knowledge spillovers and with sufficient learning by doing, we can reproduce something something similar to conditional divergence, which theoretically still which can be supported by data if we look into data over a specific range of capital, right? So that is the AK model for you in a nutshell. Okay, so in the next session we would be looking at the transitional dynamics of the endogenous growth. Okay, so if you have any questions about the AK framework, you can ask me. All right then, so we'll pick up from here tomorrow. Thank you.